As said at the beginning, and Steve mentioned it as well, edge cloud is gradually, slowly but surely becoming a reality in more and more networks. A lot of our customers are thinking about turning their COs or certain parts of their COs into small data centers, if you want. Put some compute there so they get the flexibility to run applications locally, to offer low latency or for some other reasons. And 5G is definitely a major driver here because, again, 5G is to a large extent about this mission-critical IoT, which requires processing to happen close to cell sites. Now, again, the result of all of this is actually a fairly complex architecture, right? And that's an architecture that requires a lot of automation. There are actually two aspects of automation here. First of all, it's automating the kind of orchestration of those virtual workloads, but I'm not going to talk about this. I think that is fairly well understood. We know how to instantiate those virtual workloads, how to scale them, how to move them around, how to do life cycle management on those. I think that's very well automated, very well understood. I think the area where a lot of work is needed is the networking aspect of this environment, because as this picture shows, and we are to some extent to blame for this as well as others in the industry is, we've done these initial designs assuming that those edge cloud environments are really small IT clouds which are very separated from the wide area network. And as a result, we came up with these hybrid solutions, right? Hybrid solutions where we're using traditional IT data center technology to build those edge clouds. I mean, not only data center switches and leaves and spines, I think that's all fine, but we're doing the data center virtualization using IT technologies. We're talking about EVPN using VXLAN overlays, for instance. We have a separate data center SDN controller, so it's kind of an isolated domain completely separated from the wide area network, because the wide area network, of course, does its slicing, if you want, based on IPVPNs and EVPNs that are running over MPLS and segment routing environments. So now we have this hybrid environment. So how do you automate networking in an environment like this? We solved the problem, right? We're good engineers, so we found a way to stitch those domains together. We introduced a data center gateway that does protocol translation between a VXLAN world and an MPLS or segment routing world. But the problem, in hindsight, if we look at it, it's a really complex solution, right? It's a solution that basically is very difficult to automate. You don't have end-to-end path control. It's very hard to guarantee SLAs. And there are some scalability concerns with the design as well, because those data center gateways need to be aware of all tenants in both domains. So as a result, in some designs, we've seen some scalability issues there as well. So we need a new approach, and this new approach is called NFIX. NFIX was built based on the realization that those edge cloud environments shouldn't really be treated like your normal IT clouds. They are part of the wide area network. They're typically going to be used to run virtualized networking functions. So if you accept that, then you can go to a fully or a different design, a much simpler design. And that's what NFIX is all about. With NFIX, we're basically taking wide area networking technologies, segment routing T is our proposal here, and we're extending that all the way into the edge cloud environment, which means segment routing MPLS starts from the leaf to which the VNF connects to the network. And that leaf could be a physical leaf, it could be a Tor switch. If we're talking about a high-performance SRIOV workload, it could be a virtual leaf, VRS or AVRS, if we're talking about a VirtIO or a DPTK workload, right? But I think the important thing is that segment routing starts from the leaf, from the edge cloud environment, all the way to the other endpoint in the network, which could be a physical router, let's say a cell site router, or another virtual workload. It doesn't really matter. And by the way, it doesn't require that all elements in the system need to be segment routing MPLS capable with a lot of advanced capabilities. Some don't even have to be MPLS capable at all. We can also run segment routing MPLS over UDP IP to bypass some routers that are not segment routing capable. But the important thing is it's now a uniform technology end-to-end. It's all about segment routing MPLS. So this means much simpler, no complex data center gateway functions anymore. You still have a data center gateway, more like a demarcation function, but there is no protocol translation anymore, right? So it's much simpler. We get end-to-end pod control, and we can fully automate that environment, right? The whole idea is that when a virtual workload or a VNF gets created somewhere in the network, let's say we want to put a new user plane function for our mobile gateway in an edge cloud environment because we want to offer low latency services, well, the creation, the instantiation of that instance will automate the connectivity between that UPF and all cell-side routers that it needs to connect to, fully automated. And we're doing that by basically introducing a component of NSP called the Segment Routing Interconnect Controller, which is really like a segment routing pod computation element. It will listen to all the BGP updates that originate from the VNF that gets instantiated. So the VNF will advertise its reachability requirements. It will advertise which slice it needs to connect to, basically with what the VPN instances it needs to connect to. And it can even advertise the SLA requirements that need to be met to talk to that VNF. It can do that using an abstract policy caller representation. So once we have all that information in the Segment Routing Interconnect Controller, we know everything we need to automate the connectivity. We know which endpoints need to connect to that VNF, and we can calculate which segment routing pod or which SID list needs to be populated on those routers to make sure they reach that VNF with the right SLA requirements. Very powerful, and this is ready for prime time today. So rather than spending 10 or 15 more slides diving to the details, we're actually going to show you NFIX in action. So what we're going to show you is a real use case of a 5G network, a future 5G network that we're building for some of our customers. You will see how NFIX can be used in a 5G network where we have both a centralized cloud running packet core for extreme mobile broadband services, but then also a distributed edge cloud where we're running some UPF functions for ultra-reliable, low-latency communication services. And you will see slicing as well. So each of those service types has its own slice, its own VPN through the infrastructure. So for the second demo, please welcome on stage Mustapha Aissaoui.
Okay, thank you, Rudy. Good morning. So what we're going to show in this demo is basically the automation of the instantiation of a couple of services. One is the enhanced mobile broadband service in the remote data center, DC1 here on the left. And we're going to show also a distributed edge computing or a service in the distributed edge computing data center, DC2, for the ultra-reliable and low-latency communication service. Now, one thing to do this, basically, we have 3 phases in this automation or in this process. The first phase is the discovery phase, by which basically the service definition, the overlay service definition, is being input into the Segment Routing Interconnect Controller, which is an application of the NSP. So that information is provided via either an orchestrator or via a portal, via a northbound interface. The next step is the SRIC needs to basically discover the service topology. We need to know basically the data center ID, which data center gateways exist, and also which SI router is involved in this connectivity. And then finally, we need to discover the WAN topology because, to provide this seamless automation, we need to basically have the details of the WAN topology because that's pretty much where most of the SLA constraints need to be applied. So let's look into this on the PCE user interface. You will see that network has been discovered. On the wide area network, each IGP domain is as its own color. The data center, the remote data center, is shown there, DC1, with a couple of DC gateways and 2 basically virtual leaf, the VRSs on hypervisors. And the local distributed edge computing data center has just one VRS. Now, you see that there are dotted lines on the data center topology. That's because the SRIC doesn't need to know the details of the underlay, because as Rudy said, we can tunnel over this underlay using basically MPLS over UDP. Also, we have discovered through that northbound interface a couple of slices or slice templates. One of them is for EMBB that basically has a caller 1000 that basically summarizes the constraints. One of them is actually the cost or the IGP cost, and the URLC one has caller 1001, 1001, and also has latency as the objective. So next what we're going to do is we're going to go to the next phase, which is the initialization phase. Now, what we're going to do here is that we are going to tie that information we got from the northbound interface by creating a couple of segment routing TE policies, templates in fact, to basically combine the service information with the transport information so we can actually push this into the network. And then the next step is basically to create those on the network. So let's look into this. Now, we use the service fulfillment application on the NSP, and what we do is we configure a service name, then we make a reference to the slice template that we've received via the northbound interface. Then we go next and select the endpoints of the service. One of them, of course, is the port on the cell site router, and the other one is basically the data center one, the enterprise, the user there, the tenant on that thing. We don't have a hypervisor yet or a VRS yet selected. Then we deploy the service. And then once this is done, you can see on the logs on the SRIC on the left side, there is a bunch of events that push that into the network. You log into the VSD, which is the controller on the data center one, and you will see that there is an instance of a layer 3 domain for EAMBB that has been created. There is not yet a virtual machine. On the cell site router, we automated the creation of an EVPN service that has both a layer 2 and a layer 3 component to it. And it's ready basically to be used. There's no yet connectivity to the RAN side or to the network yet, but it's ready. Next, what we're going to do is we're going to go into the automation phase. This is where all the magic happens in terms of the basically the automation part of it. So we spawn a VM in let's say the remote data center. Then we onboard the VNF, and that basically creates a bunch of activity on the data center. We get an advertisement on EVPN route, as Rudy was saying, because this is driven from the workload side of it. And that EVPN route is discovered by the SRIC, which will then do a path computation across the multiple domains and then instantiate basically the SR tunnels and connect the VLAN interfaces on the RAN side to complete the connectivity. So let's go look into this into more detail. So the VM gets created and the VNF is onboarded. This triggers basically the creation of a virtual machine port that has all the addresses that inherited from the template, and then the caller. We go to the service fulfillment interface. We see the two endpoints, the data center one there, the VRS address. This is the VNF address there. The caller, which is 1000 for the EMBB service, and there's a route target there, which is used. On the PCE user interface, you will see the paths for both directions have been created from the cell site router all the way to the data center one. And actually, it's a recursive path because there is a compressed path in the middle there over the WAN, and an MPLS over UDP component there between the data center gateway and the local VRS. Now, let's have a closer look to what happened behind the scene here. So the first thing that triggered the whole thing was the EVPN route that was advertised by the data center controller. So you see here, this is basically the prefix of that VNF, the next hop, the route target, and the caller 1000. So this is really the information we use. The route target ties back into basically the service instance that we created, and the caller pushes or points to the SRTE policy that we need to do. And this is the SRTE policy. You see source destination, caller 1000. There are two of them, actually. One is end-to-end from the cell site router to the remote VRS, and then one for the path over the WAN, which has been basically compressed using a binding SID. So we go also onto the cell site router, and we check that there was actually a policy that was pushed, and it shows here. This is the SR policy, the end-to-end one. Owner is BGP, caller is 1000, and we see the segment list, which represent the path over the network. Now we will go do the same thing in the distributed edge cloud data center, and we're going to onboard basically another virtual machine and the VNF for the URLC service. And exactly the same process again. There is an EVPN route that basically triggers the whole process here, and the service shows up on the UI of the service fulfillment application. And again, we look into the EVPN routes, into the logs here in the SRIC. You see there is an EVPN route here, very similar to the EMBB service, except that obviously the addresses are different, and the caller is 1000, which is the URLC service. Then the SRT policies that have been created the same way to actually the local data center. In this case, you will see now on the PCE user interface, there is more tunnels because now we have basically the two directions to the edge data center DC2. So that's basically shows also on the set site router, there's a second policy which is created for the URLC service with caller 1001. So basically, what happened here is we've automated the whole process from the onboarding of the VNF to basically the creation of the entire service, the path computation. This is all automated for you. The service is instantiated automatically. The import policies, export policy, the calling of the routes, everything is actually all automated basically across all these domains. And that's really the power of this solution, NFIX. Back to you, Rudy.
All right, thank you, Mustapha. Again, with this solution, I think we are ahead of the industry because, in all honesty, the first 5G deployments are very much going to be focused on mobile broadband services, obviously. I think fairly static environments, but as in the future, massive IoT, mission-critical IoT becomes important, edge clouds become important. These technologies are really going to be critical to automate that connectivity end-to-end. So just know we have the solution ready. Whenever you're ready and to engage with us on that, let us know.